Hello everyone, I'm Hui Li from the National Space Science Center. First of all, I'd like to appreciate James and John for organizing this session. Next, I will introduce you our recent work on the characteristics of MHD waves around the heliospherical current sheet. In this talk, our interests are on the heliospherical current sheet, HCS, and the associated heliospheric plasma sheet, HPS. The HCS separates the global oppositely directed open magnetic fields that originated from the Sun. They are thought to evolve from the streaming belt and are enveloped in the slow solar wind. It looks like a ballet dress in the interplanetary space. The HPS is often associated with the HCS. It can straddle, lead, or follow a HCS. Usually, the width of HPS is much larger than that of a HCS. Due to some wave generation mechanism, a variety of MHD waves are expected to evolve in the HCS and the HPS. Rich MHD fluctuations are indeed observed by some case studies. Fulon observed many alphonic fluctuations around the HCS through a comparative study of multiple satellites. Smith and Zhou first reported the existence of slow waves in the HPS observed by the Ulysses spacecraft. In addition, Dai further presented the fast waves during the crossing of a HCS. In addition to observational studies, some numerical models have been used to investigate the evolution of MHD waves in the presence of a large-scale current sheet. For example, by using a MHD numerical simulation, Mallory found that the alphonic fluctuations were weakened, but magnetonic waves were strengthened during the HCS crossings, which is probably due to the parametric decay instability. The MHD waves in the HCS or HPS have not been comprehensively investigated for statistical purposes. On one hand, the study of MHD fluctuations and subsequent potential wave mode conversion is very helpful to understand the plasma heating and turbulence evolution in the solar wind. On the other hand, the existence of wave mode conversion in the magnetic tail current sheet inspires us to perform a statistical study during the HCS crossings. To identify HCS, several criteria are applied to avoid some local current sheets. For example, the magnetic field changes size and maintains for a very long time, and we need some rapid changes in the heliospherical magnetic field directions. At the same time, a true sector boundary provided by the Wilcox Solar Observatory is in the vicinity. Based on the above criteria, 154 HCS are identified using the wind observations from 1995 to 2013. In this research, the enhanced proton density, depressed magnetic field, and increased plasma beta around the HCS are used to identify the HPS. However, there are no quantitative criteria used in the literature. For practice, we check each HCS and search for HPS by eye. And in this study, the detection steps of MHD waves are listed as follows. We first calculate the background magnetic field and then calculate the velocity parallel and perpendicular component. And then we extracting the bandpass signals for several filters. And then we can identify the segments of alpha waves and fast waves and slow waves through some criteria. And in this study, more focus is placed on investigating the effect of a plasma beta value on the magnetic wave properties and the potential wave mode conversion mechanism during HCS crossings. For the 154 events, no clear HPS signatures are found for 30 events. And according to the averaged plasma beta during the HPS, the rest events can be further divided into 3 categories. 50 events with a high beta HPS, 55 events with a moderate beta HPS, and 19 events with a low beta HPS. This slide gives the results of superposed epoch analysis for a high beta HPS situation. The left figure gives an overview of the HCS crossing. Note that a mirroring data process is sometimes performed to make the BX changes from anti-sunward to sunward. The vertical dashed red line represents the HCS crossing, and the red rectangle represents the HPS. The right panel gives the distribution of the occurrence rate of MHD waves and the growth rate of the PDI. An interesting finding is that both the occurrence rate of alpha and slow waves declines within the HPS. The physical mechanism is not clear. PDI is found to be more likely triggered in the HPS, with the growth rate significantly enhanced in the HPS, which might be responsible for the faster decay of alpha waves. Demotter found that the velocity perturbations of the slow waves decrease with the plasma beta, implying that a larger beta value may possibly result in a faster decay of slow waves. For moderate beta HPS situation, it's clear that the occurrence rate of alpha waves remains nearly stable in spite of small irregular fluctuations. However, the occurrence rate of slow waves has a significant enhancement after the HCS crossing. These results are in agreement with the simulation result obtained by Malara. For low beta HPS situation, no obvious regularity can be clearly found for the occurrence rate of alpha waves and slow waves, in spite of some small irregular fluctuations. And observational clues of the PDI are rarely reported in the literature. Here, we will show an example of PDI during the HCS crossing. It is clear that the anti-sunward alpha waves, the sunward alpha waves, and the anti-sunward slow waves coexist around the HCS crossing when the growth rate of PDI is increasing and remains at a high level for more than 30 minutes. Their wave frequencies also satisfy the three-wave resonance condition predicted by the linear theory of parallel PDI. All the results indicate the occurrence of the PDI. At last, give the brief summary. Based on the statistical study of 154 HCS, the MHD wave properties are found to be modulated by the plasma beta value. The parametric decay instability is responsible for the wave mode conversion around the HCS crossing. For example, the decay of alpha waves and the enhancement of the slow wave. And we also give the observational clues of the PDI for the first time. I think that's all of my talk. Thanks for your attention. And more details can be found in the following two papers. Thank you.